Okay, so we're going to start talking about gases and how gases move. So remember back before we start talking about these laws that gases are in constant random motion, that they do not have a defined volume, and they'll fill the shape of the container. So they don't have a defined shape either. The reason that they're in constant random motion, as we add things like heat and pressure to them, the particles start to move faster or slow down, depending on if we're adding or subtracting heat and pressure. And that is the kinetic molecular theory, that they're moving faster. So as we give them more energy, kinetic energy in motion, they will move faster. So let's start talking about the three main laws that start off chapter 14. The first one is Boyle's law. Robert Boyle was a chemist who studied the relationship between pressure and volume of gases. And so we will be doing a lab that is looking at pressure versus volume. He did this at a constant temperature. I'm not going to go through a practice problem right now. I've already set those up on the an additional PowerPoint or video. But with this, he said they're inversely related. So as the pressure goes up, the volume will go down, and vice versa. As the volume goes up, the pressure goes down. And Boyle was very consistent with this relationship, and it actually led a lot of things forward for our next two, which is Charles and Gay-Lussac's. However, I want to make sure that we understand that pressure can be measured in a few things, like 1 atm is equal to 101.3 kPa, or 1 atm is equal to 760 mmHg, or 1 atm is equal to 760 torr, or 1 atm is equal to 14.7 psi. Those are what we usually measure pressure in, and we can change the relationship based on that. Then we have Charles' law. Charles was a French physicist. He studied the relationship with volume and temperature, which was much different. And he said that they're directly proportional. So as our temperature went up, our volume went down. Volume went up. And as the temperature went down, the volume went down. So they said they're directly proportional. An example of this would be taking a balloon. We all go get balloons for people for their birthdays and for fun events. But here's the deal. If I take a balloon and it's the middle of winter and I take it outside, what happens to the balloon right away? Well, it shrinks. Temperature decrease, so does the volume. The particles are closer together. So we start looking at the kinetic molecular theory. As we take temperature away, the molecules will shrink, or they stop moving as much. They have more potential energy than kinetic energy. So as we decrease the temperature, we're decreasing the amount of kinetic energy, which means the particles are closer together, which means the volume is less. And as we increase the temperature, we're giving them kinetic energy, and so the particles can move further apart, therefore increasing the volume. Wonderful, right? Gay-Lussac looks at the relationship between temperature and pressure at a fixed volume, so the volume can't change. This is a great example of a pressure cooker. How many of you guys have moms or grandmas or aunties or somebody that uses a pressure cooker for canning? The volume of the container inside of the pressure cooker cannot change. It's a metal container. It cannot change. However, we change the pressure by increasing the temperature. So in a sealed device, you can increase the pressure on that device as you increase the temperature on that. And so if we take a pressure cooker, we put it on the stove, it's all sealed up, you can see as the temperature is going up, because there's a temperature gauge on it, your pressure gauge is also going up. Those particles are moving faster as we add temperature to it, and when they're in a container that has a fixed volume that cannot change, then they'll just push. This can also be a problematic, and you should know this relationship for a really good reason. If you would have a closed container and there's any type of abnormality to it. So a great thing, if I'm in a submarine, that submarine is at a fixed pressure and temperature, hopefully. But as I go down, the pressure and temperature are going to change. I don't want the internal pressure and temperature to change, just the external pressure and temperature is going to change. If there's any crack in the exterior of that container, it crushes like a little can in somebody's hand. So we have to make sure that we understand that pressure-temperature relationship. And as the pressure increases, the temperature increases as well. And these forces will push on each other.